Okay, let's get going. More exciting things to learn about probability. Today, we're going to get more into the principles of using Bayesian inference, how to apply, Bayesian quantitative methods. So we have to have the disclosure thing that I work at Columbia. I also work outside of Columbia using STAN, and according to Columbia University policy, that creates the appearance of a conflict of interest that you should be duly aware of. We are actually going to be talking a little bit more about STAN language today. So the reading for today started to get into the Doing Bayesian Analysis book by John Krushke, who's a psychologist. So we'll see a little bit of this from a psychology perspective. The reading for Thursday is from econometrics book. So we'll see it a little bit from an econ perspective. And of course, do plenty of political science examples over the course of the semester as well. So you can see how the Bayesian approach can be applied broadly throughout social sciences and also obviously including marketing as well, certainly in some non-social science things as well. But I think it works especially well for social science applications. And I think social science is one of the areas in which the frequentist approach and like supervised learning approaches do not work that well. Anyway, just some quotes from the book. Krushke says on page 15 that possibilities over which we allocate credibility are parameter values in meaningful mathematical models. And so what does that mean? So we have possibilities for what the parameters could be. Those all consist of a parameter space, which we denote with theta in contrast with a sample space for random variables that are data, which we'll denote with omega. Anyway, the parameters, and so far we've only done examples that have one parameter, but in general we could have multiple. So I'll denote those with theta. There's some model for the data generating process for the outcome variable of interest y. And those can be understood with the parts of Bayes' rule for a continuous random variable theta, or our beliefs about the continuous random variable theta, given the observed data that we may collect. And so we just have, the left-hand side of Bayes' rule is equal to prior PDF for theta marginal times the conditional PMF or PDF for the data given theta. And then the denominator, we have a marginal distribution PDF or PMF for the data. This is, before you see it. We can represent the denominator as an integral of the numerator over the entire parameter space. And in general, that could be a double or a multiple integral rather than just a single integral. And the numerator we can understand as a PDF for the joint distribution of the parameters and the outcomes of interest. And then, but those parameters, theta, even though I've sort of written them in a generic form here, in order for you to specify reasonable prior distributions about them, they have to be at least somewhat interpretable in the context of a model that you want to estimate to explain some outcome y. Moreover, since theta appears in the conditional distribution for y, you can't really understand or interpret what theta means or what would be reasonable values for it before you see the data without understanding the distribution that you're using for the data generating process y. So both of these things have to be understood together and collectively in order for you to come up with a reasonable model and to be able to interpret those parameters enough to be able to specify reasonable prior distributions for the unknowns and reasonable distributions for the data given the unknowns. And so Krushke goes on to say that Bayesian inference is a reallocation of credibility across possibilities after observing new data. And so always have to keep in mind that probability is, basically arithmetic and, some calculus in the continuous case with these sort of special case functions that are non-negative, and they either add up to 1 in the case of a discrete space, or they integrate to 1 in the case of a continuous random variable. So you always have like one unit of probability that can be allocated throughout the parameter space theta. And, you might have some distribution for how you think it's allocated before you see the data. And then once you see the data, you're compelled to change that allocation to something else. So if it's like over here, you might, squish the distribution in and push it over to the right a little bit. But every time you see new data, that forces you to update your beliefs about what the unknowns are, which is to say reallocate your credibility in light of the new information that you've observed. And the Bayesian process is basically a organizational tool to make sure that your beliefs about the data are always consistent with all our beliefs about the parameters are consistent with all of the data that you have observed, and then just following through the implications of that. And so, as I was saying, the prior beliefs have to be expressed in terms of a probability distribution, and in particular, when using Stan, a PDF representation of that distribution, or really the logarithm of it. Anyway, once you condition on the available data, it maps your prior beliefs into posterior beliefs by multiplying, by the other or the ratio of the other two terms to obtain this conditional PDF for the parameters, given the new data that you've obtained since you specified your prior. And so that's sort of a thematic overview of what we're trying to do with Bayesian analysis. Always keep our beliefs about the parameters to be, consistent and updated with the data that we have observed. And that's just a very general approach for science and for social science in particular, where there's all kinds of things that we don't know represented with parameters, but we have lots of opportunities to get data to update our beliefs about those parameters. Questions about that so far? Okay. So there's a good question on Campus Wire about relating these things, talking about the likelihood function, which reminds me that you should be participating more on Campus Wire. We've had some good posts, but haven't really had a lot of follow-up to those good posts, where you can add additional questions and things like that, get more clarification. So I would encourage you to do that. The question on Campus Wire, I posted a response there, but I think we should talk about it in lecture as well, is, what is the likelihood function? How does it relate to a PDF, etc.? So you can think of a likelihood function. It's the same expression as a PDF or a PMF, depending on whether you're continuous or discrete case. But there's sort of three distinctions that you need to keep in mind when talking about a likelihood function. So when we have some PDF or PMF, f of x given theta, we think of x, capital X, as being a random variable, and theta is being given, even though it's typically unknown and something we want to estimate. Now we can take that same expression and we call it a likelihood function as a function of theta evaluated only at the observed x that we have in our data set. So when it's a PMF or a PDF, you can think of it as, well, before the data are observed, I have this expression that tells me the probability or the slope, at any x. But once you've collected data that you want to condition on, you're only evaluating this function at that particular value of x, not all values of x that would be possible in the sample space omega. But it can nevertheless be considered a function, but now it becomes a function of the unknown parameter theta rather than a function of x in the mathematical sense of a function mapping from one set to another set. There's no mapping from x once you've observed the x. It's just something that you condition on. And so before you observe the data, f of x, or the sum, it integrates to 1, or it sums to 1 over omega, the sample space of x. After you've observed x and you're only evaluating this function at the x that you observe, now taking it to be a function of theta, well, that function is positive, always positive. And so if you integrate it, it's going to be positive. But if you integrate it over the parameter space for theta, it doesn't integrate to 1 in general. And so it's not a PDF of theta. It's just a function that happens to be positive. So you can remember things that way. Oftentimes when people say the likelihood function, what they mean is not the likelihood function for a particular observation, evaluated a particular observation X, but rather for n conditionally independent observations X. And so what they mean by the likelihood function is actually the likelihood function over the whole data set. But if those X's are conditionally independent, given the parameters before they were observed, then the likelihood for the whole data set is just the product of the likelihood contributions for each of the observations in that data set, but again considered to be a function of theta and only evaluated at the observed X's. Finally, when people say likelihood function, what most of the time they really mean is the log likelihood function or the natural logarithm of the likelihood function. And since the logarithm of a product is the sum of the logarithms, if we just take the logarithm of the likelihood function, we get the log likelihood function. But a lot of people just say likelihood function when they mean log likelihood because they're mostly interchangeable. And insofar as they're not interchangeable, people only really use the log likelihood version rather than the plain likelihood version. But mathematically, it works out either way. But in terms of implementing it on a computer, all software, Stan included, is going to be dealing with the logarithm of these likelihood functions rather than the likelihood function itself for numerical stability reasons. So are there any questions about that or the difference or the similarity between, you know, a PDF, which is a function of X, and a likelihood function, which is the same expression, but conceived of as a function of the unknown parameters, theta? All right. So I don't think you'll see this phrase used anywhere, but one way it makes sense for me to think about these things is the likelihood function of theta is the sort of ex ante probability density or mass function. So before you observe this particular X, what would be the probability of observing that X? Then you can think about it that way, but always have to remember, you know, we're thinking of it as a function of the unknown parameters rather than the observable values X. So X ante PDF would mean the same thing as likelihood. Kurski talks about sort of steps of a Bayesian analysis, and you'll see similar sort of things in like every Bayesian textbook, maybe with a little bit of emphasis, but difference of emphasis. But as far as what we're going to talk about in this semester, I would sort of break it down into 5 or so steps. First is to formulate a generative model by classifying the concepts that you want to be involved in your model as being either exogenous or endogenous, and simultaneously either being known or unknowable. And so every concept that fits in the model is going to fall in, you know, one of those 4 categories. And we'll talk more about that next. Once you have a model, draw from the prior predictive distribution. So what your model implies the outcome variable should look like in terms of its marginal distribution before you see the new data or before you collect the new data. This is good because you can test that the software that you get, like Stan, is working correctly on this data that you've simulated before you try it on data that you've collected. Also, at this point, you know, you've sort of established where your priors and stuff like that are. Now might be a good time to pre-register your analysis if that is sort of the expectation within your subfield. It eliminates or mutes some of the criticisms of, you know, the Bayesian approach. So you could always just like change your priors after doing the analysis in order to conclude that you were right or whatever. Step 3, obtain new data, you know, or at least new data on the endogenous known outcome variable that you are trying to measure. Condition on that new data using Bayes' rule to obtain the posterior distribution of the unknowables, conditional on the known data. And if you're doing this in Stan, which you should, this may very well, you'll get some warning messages, and you should fix those. But we'll talk about what those mean, because when Stan is not working so well, it's pretty good at telling you it's not working so well. And so you need to heed those warning messages and take some steps to overcome them, which is actually an advantage because other software that you can use for Bayesian analysis isn't going to be capable of detecting that something went wrong just from the output or the process that you get. And then once you've gotten, you know, a pretty solid posterior distribution of the unknown parameters given the known data, you can then draw from the posterior predictive distribution what your model implies future data on the outcome should look like given your updated beliefs about the parameters. You can compare that to the data that you have. You can use that to evaluate your utility function and, you know, take the expectation over that for various decisions that you might want to make, you know, formulate a conclusion, etc. And so those are the sort of 5 basic steps. We'll walk through most of these today, but sort of every session from here on out is going to be involving, you know, one or more of these steps in the so-called, you know, Bayesian workflow, or at least the Columbia version of that. And all this can be done for multiple models. Remember, we said, you know, among the 4 sources of uncertainty, which model or set of models would be best. And so this can be done for multiple models. You just don't want to let the posterior distribution of one model influence your prior distribution for another model if you're evaluating these all with the same outcome data. So generative models. What do I mean by a generative model? A generative model is one that you can simulate from. And so in order to draw randomly from your prior predictive distribution, you have to have one of these general models, generative models. And without them, then there's no updating your beliefs. So Bayesian, from a Bayesian perspective, a generative model is basically saying, before we see the data, how do we represent our beliefs, both about the unknown parameters and about the outcomes that we're going to collect data on shortly. And like I said on the previous slide, when formulating one of these models, you can classify things based on whether they're known or unknowable and whether they are exogenous or endogenous under the model. So we'll start with the one in the bottom left here. The outcome variable that you're trying to explain is, you know, by definition, endogenous. This is something that the model is trying to, you know, provide insight about by explaining how it was generated. But it's something that is knowable or known, in fact, once you collect data on the outcome. Does somebody vote, or, you know, whatever it may be. So you're formulating a model in order to ultimately explain the data generating process for this outcome. And so you can get data on that, and so it's knowable or known, but it's endogenous to the model because it's something that you are trying to explain. Those endogenous outcomes can and should be a function of some unknowable parameters. Now, unknowable is kind of a strong word. By that, I mean we're never going to be completely certain as to what regression coefficients or means or error standard deviations are. We can estimate them with like less or more precision, but we're never going to know them with absolute certainty. So we put them in the unknowable column. But these, you know, regression coefficients, other parameters like that, we consider to be exogenous, or at least in, you know, simple models of them, because we're not trying to explain, where the beta coefficient on the education variable comes from. That's not what our model is intended to do. We're just saying, it's something that's provided by nature, and hence goes in the exogenous row. In the top left here, we have exogenous knowns. That would be sort of the sizes of things, like how many observations you have, how many predictors you have, and other information that you need in order to specify your prior beliefs about the unknowable exogenous parameters. So we say the parameters are not known, indeed not knowable, but you do need to know what you believe about those parameters and be able to represent that with prior medians or prior modes, things like we talked about last week with the Ebola example. But we're not trying to, with this model, explain, how the predictors come to take whatever value they are, or trying to explain why one person has this prior mode and another person has that prior mode. It's all just sort of taken to be given from the outside of this model. And that emphasizes an important point with the Bayesian analysis that, okay, an input to this whole thing is your prior beliefs about the unknown parameters, and two people can obviously differ on that, but the Bayesian approach is basically the right thing to do, irrespective of what exogenous prior information you're coming into it. Even if you're wrong, or both sides are wrong, the right way to update wrong beliefs is with Bayes' rule. And so we're not really disputing or that much or caring that much where or how you came to believe whatever you believe before observing the data. Finally, in the bottom right, we have unknowable and endogenous things that our model implies, but we don't and indeed can't know exactly what these are. These could be intermediate parameters. They could be predictions of future data. They could be, utility under different states of the world. So these are things that are unknowable because they're going to depend on unknowable parameters. So, the utility function, okay, depends on these unknown parameters, etc. If we knew the unknown parameters, we could evaluate our utility function when we know what that is. But we don't know for sure what the unknown parameters are. So we have uncertainty in our utility function, and we need to take that into account and, take the expectation over that, etc. So anything that depends on the unknowable parameters is also going to be sort of marginally unknowable, but conditionally knowable. So if we have a distribution, a posterior distribution for the parameters, we can stick that in to the function that gives us predictions or utility, whatever, and sort of conditional on that distribution, then these functions become known. But since we don't know the parameters for sure, they fall these in the unknowable bucket as well. And so each of those four things is going to be involved when formulating a model that you can simulate both the unknowable parameters and the outcomes from jointly. So we might think about a simple sort of thing that we might do in the data generating process, or in social science, is think about a data generating process for how many people live in an apartment or a house, just some residential unit, or etc. And we might think there's some overall mean for the number of people who live in an apartment or a house, and then there's random variation around that mean. So what would that look like in this schematic? So the endogenous known, y, the outcome that we're going to collect data on, but we want to think about it in advance, is the count of the number of people who live in this or that residential address. So that's the outcome that our model is trying to explain. The exogenous unknowable parameters, or parameter in this case, there's only one, the expected number of people in a residence, and then the actual number of people can randomly vary around that expectation. The exogenous knowns would be, the size of our data set, the number of residences that we're going to collect data on. Our model is not trying to explain why, some people get bigger data sets than others. That's just something that comes in from the outside. We might also want like a prior mode or a prior median to use in our prior distribution for mu, which we're estimating the unknowable parameter. And then finally, the endogenous unknowable, the predicted number of people that would live in some future residence that we haven't collected data on yet. So our predictions for some future thing, that's unknowable. But if we had a posterior distribution for the parameters, we could get better predictions for that thing. So you can see how each of those falls in one of the four squares, but we're still going to have to choose a prior distribution for the exogenous unknowable parameter mu and a probability distribution for the endogenous known outcome variable y given mu. Right? Everybody see how we did that? How those pertain? Questions about the difference between exogenous and endogenous, known and unknown, which goes in which box, how they map onto the pieces of Bayes' rule? Okay. So, sort of figuring out how to complete the model from here, drawing from the predictive distribution under your prior, so before you see the data, predicting what the data will be once you collect it, is a good way to check that your prior distributions are reasonable that you chose. So if you say, okay, I'm going to try this prior, well, evaluate the predictions for the data you're about to collect that are implied by that prior and see if that distribution looks like the distribution you anticipate the data will be when you actually collect it. If there's a mismatch there, then that might be something that would cause you to rethink your priors before you actually, get any data. And so that can be a good way to check that your priors are reasonable. Also, drawing from the predictive distribution of the data before you observe it, and then using the software to fit your model to that predictive data that you've just simulated is a good way to check that your software is working correctly, because that should not systematically change your prior distribution if you condition on data that was generated by your model. And we'll talk more about how to do that more formally in later weeks of the course, but you always want to be able to check that your software is working well, because a lot of software doesn't, at least in some cases. So in this case, our outcome is the count of the number of people who live in an apartment or a house or whatever. So we can use the Poisson distribution, which is like the only distribution we've learned so far for dealing with a sample space that's all non-negative integers. And it has unknown parameter mu. So the Poisson distribution may not be super appropriate, but it's the only one that is sort of mildly appropriate that we've learned so far. Now, the sample space for a Poisson distribution is all non-negative integers. And that can still work for something like the number of people who live in an apartment. There's no theoretical upper bound on the number of people who can live. There might be a city regulation, but like a house or whatever. There's no theoretical upper bound on the number of people who can live in a house. And so we sort of treat it as an unbounded integer, even though for all practical purposes, it'd be very rare to see like a double-digit number unless it was some sort of like group home or something like that. Even then, they would have individual mailboxes. So yeah, certainly we're anticipating a single-digit number here, but there's no theoretical upper bound. And so perhaps the Poisson distribution with a fairly low expected value mu could be reasonable for something like this. So when there's no necessary upper bound on a count, you'll often see people use Poisson distribution, and that has this unknowable expectation, mu. Okay. So how would we write the logarithm of the probability of observing n Poisson independent random variables that each have expectation mu? Which is to say, how would we write the log probability of observing n counts for n different apartments or houses of the number of people who live there? What will we do to get the log probability of that? So how would we come up with that? Patrick? The individual logs of what? PMF of the Poisson. Right, and what is the PMF of the Poisson? That we learned on like the third session, maybe fourth. Yeah.
E to the something over the factorial.
We got the factorial part, right? So this expression here is, I think, what Catherine was looking for. E to the negative mu times mu to the yn. That would be the contribution for the nth observation, divided by the factorial of yn. And since e to the negative mu, it does not involve yn, we can pull it out front. But we have the product from the first observation to the last observation. So that's n copies of e to the negative mu multiplied together. Or to simplify that, e to the negative n times mu. That's our first piece here. Then we have the product from 1 to n of mu raised to the power yn. And similarly, we can simplify that as mu raised to the power of the sum of the observed y's. And then finally, we have the product of the reciprocal factorials. And so if we take the logarithm of that, the logarithm of a product is the sum of the logarithms. And so e to the negative n times mu, the logarithm of that is just negative n times mu. And then the logarithm of mu to the raised to the power of the sum of the y's is going to be sum of the y's times the logarithm of mu. And then the logarithm of the product of the reciprocal of the factorials is just going to be subtracting the sum of the log factorials, remembering that the logarithm of a ratio is the difference of the logarithms. Logarithm of the numerator, logarithm of 1 in the numerator is just 0. So we have 0 minus the logarithm of the denominator. And so that can just pull the minus sign up front, minus the sum of the logs of the factorial terms. So we're always working with the logarithms of these things because it gives us better numerical stability, but it also can make things easier when there's some simplifications we can do as a result of taking these natural logarithms. Does everybody see how I did that there? Questions? But we're still going to need, in order to draw from this predictive distribution, we're going to need a prior distribution for the unknown mu that we can draw from. And we can use the draws of that to make draws, predicted draws of the outcome. So in order to do that, we're going to learn a new distribution, the gamma distribution. So if our parameter space is all non-negative real numbers, and we have some constant a, which is positive, the PDF of the so-called unit gamma distribution, or maybe standard gamma distribution, can be written as f of theta given a, 1 over the gamma function evaluated at a. So the gamma distribution involves the gamma function. 1 over the gamma function evaluated at a times theta raised to the power a minus 1 times e raised to the power negative theta. So that is our PDF. What would be an expression for the gamma function evaluated at a? Yeah. Not something that requires a lot of pencil work, but it's a fundamental idea. So we know, because this is a PDF, it has to integrate to 1 over the entire parameter space, which in this case is the non-negative real number. So we're integrating this from 0 to infinity. But this piece here, 1 over gamma evaluated at a, does not involve theta, which is the variable we're integrating over. So I can take my eraser and pull it outside the integral. And if this times the integral is equal to 1, I can take my eraser again, erase this piece, erase my 1, and it's just gamma of a is that definite integral. And that just follows from this, fundamental starting point of probability with continuous random variables, that their PDFs integrate to 1 over the whole sample space. So any of these terms that you see in a PDF that do not involve the random variable in question, you can just pull those outside the integrals, and all they do is make the thing integrate to 1. Questions about that? Yes.
I guess a little bit because this is a PDF, right?
Uh-huh.
And then we're integrating it over.
Uh-huh.
But I thought, like, maybe 15 minutes earlier, like the PDF, it's one theta is, but then the likely function is theta.
Right. So we can have PDFs for either observables that we're modeling, or for parameters that are part of the model.
Okay.
So here we're going to be using the gamma to specify a prior on a parameter. But we also have PDFs, PMFs, etc. for data outcome variables given parameters. So you just need to keep straight in any particular usage of this. Okay, what's the random variable we're talking about? In this case, it's theta. So I'm integrating over theta. Anything that doesn't involve theta, I can pull it out. I can move it to the other side, whatever. But the terms that do involve theta, you know, I can't just pull this out of an integral. But the ones that don't involve theta, I don't. Okay. So suppose that mu is equal to theta divided by some constant b, where b is also positive. What then is the PDF for the distribution of mu? This does require a tiny bit of pencil work. Not that much. Just a little bit. What do you got? So what do we need to do to solve these problems involving transformations? Sanjana? That's part of it. So what do we replace the theta with? Correct. So that's just one part of it. What's the other part of it that we need to do in order to make sure our PDFs integrate to 1 over the space of mu? Huh? No, not a log transformation. But with any transformation, any change of variables, any integration by substitution, there's always a chain rule piece. So as we correctly said, if mu is equal to theta divided by b, then theta is equal to b times mu. And we can replace every occurrence of theta with b times mu. But in order to make this admissible for a continuous random variable, in order to make our PDF integrate to 1 over mu rather than theta, we're going to have to utilize the chain rule multiplied by the derivative of theta with respect to mu, which in this case is just b. So we take our PDF for in the unit gamma distribution for theta given a. Everywhere we see a theta, we replace it with a b times mu. And then multiplied by b, the whole thing. So we get b times mu raised to the power a minus 1 over here. And then we have one extra b out front. So we, in the end, we get b to the power of a divided by the gamma function evaluated at a, multiplied by mu raised to the power a minus 1, multiplied by e raised to the power negative b times mu. So there's 2 steps to doing one of these transformations, or the sort of preliminary step before you do either of the first 2 steps. Figure out how to express what you do know the distribution of, which in this case is theta, in terms of what you're seeking the distribution of, which in this case is mu. So find that inverse transformation from mu to theta. Then do the substitution and multiply by the derivative of that inverse transformation. Then you'll get a PDF that integrates to 1 over the sample parameter space of mu. If you forgot the chain rule term, it's not going to integrate to 1 anymore. All of your answers will be wrong. Questions about that? Yes.
Can you explain again why do we need this derivative? I know we need it to
One way to think about this is like when you do integrals by substitution and you have to do a change of variables. Here we're doing the same thing but in reverse. Rather than trying to figure out what an integral is, we're trying to figure out, what is the slopes that need to happen in order for that thing to integrate to 1. And so we're going to need this additional piece. It ought to be fairly clear, or at least if you work it out a little bit. So if you omitted the b and just did the integral of the rest, it can't come out to 1 if that first thing comes out to 1, unless you put the b term on top of it. But you can see this formally if you write the CDF in terms of mu and then differentiate with respect to mu. However, in this case, the CDF of the gamma distribution doesn't have an elementary form. And so you can't really write down the CDF in any sort of useful way. But we did it last week with the normals and the log normal and stuff like that, where we do have elementary expressions. And you could see how this is implied when you differentiate the CDF with respect to mu, the variable whose distribution you want, to make it come out to 1. There's a chain rule piece in there. Okay, so this is the PDF of the general gamma distribution, has shape A and rate B, although sometimes you'll see the gamma distribution parameterized with the reciprocal of the rate, which is known as a scale parameter. And in some ways that's better, but we'll stick with the parameterization in terms of a shape A and a rate B. The expectation of a gamma distribution is A over B. If you work out that integral, comes out to A over B. And the mode can be written as A minus 1 divided by B, provided that A is greater than 1. So the numerator of that expression for the mode stays positive. Since the gamma distribution is defined on a parameter space, all non-negative numbers, if A was between 0 and 1, then A minus 1 divided by B would be a negative number. And it doesn't make sense for the mode of a random variable whose parameter space is all non-negative numbers. It wouldn't make sense for the mode of that to be negative. Does not even in the parameter space. So we'll assume A is greater than 1. So what would you think are reasonable values of capital M, the mode, and the expectation of mu to use in your priors for this example, the count of the number of people who lives in this or that apartment or this or that house? So what would be a reasonable value, your best guess for mu? And that best guess is your prior mode, capital M. What would be a reasonable value for that? Ryan?
4.
4. Doesn't have to be an integer.
4.2.
4.2. 1/10 of 42. Okay. So then what would be, if that's your mode, prior mode, do you think the prior expectation of mu should be less than, equal to, or greater than that prior mode? Okay, it's your prior, so.
Well, I mean, by the definition, shouldn't it be larger?
Yeah, basically. For these variables like, the count, we're ultimately trying to model that have this skewness to them. So, a lot of places is just going to have like 1 or 2 people in them, but, a few, you're going to have like 8, 9 or whatever living there. So in a situation like that, you tend to get an expectation that's larger than the mode or the median. So we should be thinking about values for the expectation of mu that are greater than our prior mode. So, 4.5 maybe, something like that. Okay, so if that's our prior mode and the expectation of mu under our prior, how would we use that to get the shape parameters A and B that we need in order to use our shape parameter A, rate parameter B that we need in order to use the gamma distribution as our prior? Does that help? So if M is equal to the expectation of mu minus 1 over B, what's B? Algebra, people. Solve for B. Algebra involving subtraction. And like 1 division. You need to cancel. It's not bad. Patrick. All right. We got B. Halfway there. What's A in terms of expectation of mu and M? Right.
M over expectation mu minus M plus 1.
Or right. So it's B times the expectation of mu, and then just substitute in that. Right. Which is what you said. It didn't sound like what I was thinking it was going to be. But yes, that is true. All right. 2 equations, 2 unknowns, given a prior mode and a prior expectation, you can get the shape A and the rate B that you need to plug in for your gamma prior. Could use Wolfram alpha, but honestly, it should be faster to solve it on paper than it would be to like type in wolframalpha.com and then these equations. About the simplest mapping from mode and expectation to shape and rate that there is for any distribution. Questions about all this? So we've said, okay, we're going to use the gamma distribution for whatever reason with our prior. We've said what our prior mode and our prior expectation is. We've figured out the equations relating those to the shape parameter A and the rate parameter B that we need for the gamma, and we're ready to go. All right? Yes, Mark.
So for the
So if you integrate the first thing there, that integrates to 1 over theta. So that thing, d theta, that integrates to 1 from 0 to infinity. This one, the general gamma PDF, with 2 parameters, a and b, that integrates to 1 over d mu. Right. Because we did this correctly. But we did correctly means the things integrate to 1. So we've gone from a unit gamma distribution or standard gamma distribution that just has 1 shape parameter A to a more general and more useful gamma distribution with shape A and rate B. You can also understand the unit gamma distribution as a special case of the general gamma distribution when B is exactly 1, in which case this just cancels and you get back to where you started with. Or the ones get multiplied by something and whatever. So unit gamma, special case, general gamma with B equal 1, but B doesn't have to be 1. Indeed, with these values of the expectation and the prior mode of mu, B is not going to be 1. But it could be. Yes? Mu is unknown. So we don't know what is the expected number of people who live in particular apartments, but we know what we believe about mu. And that's why I got, a couple numbers. You could believe something different from what Brian believes, but you have to know what you believe. You don't have to know the truth about mu. That's why we get data. But you need to know what you believe and to be able to express what you believe with probability distributions, such as the gamma distribution. So if you say, okay, I believe it has this prior mode, this prior expectation, then you can use the gamma distribution as your prior for the unknown mu. So you don't need to know the truth. You'll update to get, closer to the truth. But you do need to know what you believe and to be able to express to what you believe using the language of probability, which is to say with a PDF. There's different choices, but gamma is a pretty good one here. So in terms of getting draws from the posterior distribution, we can do what we did last time with the Ebola example and whatnot by defining this function in the Stan language, exposing it to R, and then calling it. Now, I should say that this is just one aspect of Stan. We're going to be using Stan a little bit more intensively as the weeks go on, but we're not going to be really using the full Stan until April. So what we're starting with is just, can you do one function? And this one function is going to return me a vector of draws from the posterior distribution. It's called residences underscore RNG because it's going to be drawing random numbers from that posterior distribution. It takes as inputs an integer s, the number of draws I want, like 10,000 or so. It takes as input a real number, capital M, for your prior mode about mu under a gamma distribution. It takes another real number for your expectation of mu, which I call in this function emu. And it takes a collection of counts, y, that we observe. And y doesn't have to, or in general, it wouldn't be just a single scalar, like one count, one residence that you go and figure out how many people live there. It can be of size n. And so that is a one-dimensional integer array in Stan. And that is indicated by int, open bracket, close bracket, to say there's going to be more than one int is part of y. In fact, there's going to be n of them. So those are the arguments to my function. Inside the body of my function, I just do these expressions here, mapping from emu and m to a and b. I pre-calculate the sum of the y values, because that's just a constant, and that's, you'll see below, the constant I'm going to need. But we don't want to recalculate that every time we go through a while loop if we can just calculate it once at the beginning. I declare a vector of size s that's going to hold my posterior draws and initialize a counting variable little s to 1 and use that in my while loop. I'll check that A and B are satisfy these inequalities, but you have to do these things after you've declared everything that can be declared before the while loop. Inside the while loop, as long as little s is less than or equal to big S, I get to declare more things after any opening curly brace. So here I had an opening curly brace. I can declare new symbols. Inside the curly brace that defines the while loop, I can declare more new symbols, such as mu tilde, which is drawn from the gamma distribution randomly with shape A and rate B. And so I'm going to call that mu tilde. Then I use the value of mu tilde in order to draw predictions of the data. So first I'm going to initialize an integer array of size, the same size as y. So to initialize an integer array, you put the size after the symbol name. So this symbol is called y tilde, and it's of the same size as y. That's different from initializing a vector, where you put the square brackets after the r in vector. It's a little bit confusing, but implicitly a vector in Stan is going to contain real numbers. There's no such thing as a vector that has integers in Stan, although there is in R. So specifically in Stan, if we want to have multiple integers that are associated with the same symbol, we declare it as an integer array, and the sizes of arrays go after the symbol name, in this case y tilde. Then I'm going to loop from 1 to whatever the size of y is, so capital N, and I'm going to fill in y tilde, each element, with a draw from a Poisson random number generator using my realization of mu tilde that I just drew from the gamma distribution. So this conditions on mu tilde between the marginal realization of mu tilde and the conditional realizations of y tilde, I now have a realization of the joint distribution of my unknown mu and my predictions for what the data will look like. I then evaluate whether the sum of the y values that I observed, this constant that I calculated once, is the same as the sum of the y values that I simulated from the prior predictive distribution. If so, stick mu tilde into the sth value of post and increment s by 1. If not, just go on to the next iteration of the while loop. So you can see what we're doing here. We're drawing from the prior distribution, gamma, drawing from a gamma prior distribution, but we're keeping those draws selectively. We're keeping those draws if they satisfy a condition, and only if they satisfy a condition. And that condition is, does the sum of my predictions match exactly the sum of the values that I observe in my data in the real world? If so, keep that draw. If not, go on to the next iteration of the while loop until I've filled up post with capital S good draws. And so you can see if you're drawing from the prior distribution, but you're keeping those draws selectively, conditionally, and your condition involves the observed data that you've collected, then the distribution that you get out at the end is going to be different from your prior distribution that you drew these things from and then selectively kept them. So your posterior distribution is going to move one way or another compared to your prior distribution as a result of conditioning on the y's that you observe in your data set. And that's how you can use, and it really only works well in this case in binomials and whatever, where we have integer outcomes. But you can do that to draw, in this case, from the posterior distribution. and then you just return those draws sorted when you break out of the while loop. All right? So it's similar to what we did with Ebola, but now we have a count outcome, albeit a pretty smallish count outcome. This wouldn't be efficient if we were dealing with big counts, because the probability that these would be exactly equal would be really small, and we'd throw almost all our draws of mu back. This does take like 1,000 iterations of the while loop in order to get like one good draw. But in C++, it goes so fast that you don't even notice. So it's not efficient, but it's okay for this purpose. But the real thing is to understand the concepts being reflected in the stand code here. So does anybody have questions about that? Okay.
What, based on the previous slides, what the link between gamma range, the real mu to the gamma range and the Poisson range?
Right. So this line here is a draw from my prior distribution. So mu tilde is going to be a real number. It's going to be a positive real number because it's drawn from the gamma distribution. Then I use that realization to draw from the Poisson distribution, conditional on this realization of the expectation. So I draw the expectation, and then I draw predicted counts given my realization of the expectation from my gamma prior. And then I see if those predicted counts sum up to my actual count. If so, I'll keep that draw as one of my posterior draws. If not, I'll just move on to the next iteration of the while loop. This way we can selectively keep draws from the prior and thereby obtain draws from the posterior. Well, the gamma distribution or the Poisson distribution is conditional on some expectation that you're trying to estimate. And the gamma distribution is a plausibly good prior distribution for that unknown expectation that you're trying to estimate. Other than that, there's no essential relationship between them. Gamma is on a parameter space of all positive real numbers. Poisson is for a sample space of all non-negative integers. So they don't even have the same spaces, but they go together pretty well. Patrick.
So Y tilde is like an array of the number of people in each simulated house.
Yeah.
And you're only keeping the ones that sum up to your true
Observed. Yeah. So let's say I observe 10 houses, count the number of people in them, add it all up. Then I simulate 10 houses. If my simulation exactly predicts what I observe, keep. If not, do it again until you get as many capital S as you specify. So I have this stand program. It's on Canvas. I take it, I call the expose stand function in the rstand package that compiles it to C++ and enables me to call it from R. I'm going to use little different values of M and emu, but you can use whatever ones you want as long as they're valid. Here's my Y. I just made this up, but it has 10 houses or whatever. I want 10,000 simulations, so I call my residences RNG function with S, capital M, emu, and Y. I get back 10,000 draws from this posterior distribution. I can then plot the CDF of them. So the posterior CDF is in black. My prior CDF, calling the gamma p gamma function, is in red. And I can see by conditioning on these data, I've shifted my CDF to the left and made it steeper compared to my prior CDF. Conditioning on data reallocates the probability, shifts it over, compresses it down. I get a new distribution as a result of conditioning on that data. And I can compare the CDFs from my prior and my posterior. Same as we did before. Another way to do this would be to define a function like this, which is the numerator of Bayes' rule. So here I'm going to take in a vector of possible values of mu. The rest are the same. I get A and B, declare an integer k, which is the size of my proposed mu vector. Calculate the logarithm, because I'm going to need that twice. Logarithm of mu, that's going to be a vector of the same size as mu is. Then I'm going to calculate the logarithm of my gamma prior, which is just a minus 1 times the logarithm of mu minus mu times b. Here I omitted the stuff about the gamma function and the constant, because I'm just going to divide anyway, and those constants would cancel each other out. Then I calculate a vector of size k, log likelihood values, by taking the logarithm of the Poisson likelihood. So that comes out, omitting the factorial term, sum of y times log of mu minus mu times the number of observations. Again, the constants are going to cancel anyway. And then I do that in log units, but I return it, the anti-log of that, so it's in probability units, but this is more numerically stable. I expose that to R, and then I call the integrate function in R, evaluating this kernel function. I go from 0 to infinity, and I supply m e mu and my observed value of y. It does that integral numerically with little trapezoids. I get back some value. It's real small. I don't care that much about what it is, really, because all I'm going to do is take the kernel function that I just defined, divide by the denominator. The denominator is just the result of doing that numerical integration. So it integrates to 1. So that's the black curve here. I can contrast, that's a PDF, posterior PDF. I can call the d gamma function at A and B to get my prior, and that's represented by the red line there. I can also do this analytically. We're not going to have time to do that today, but it's on the previous slide. So it turns out in this case, the posterior distribution is also going to be gamma, like the prior, but the posterior distribution is going to have updated shape and rate parameters, A star and B star, where A star is equal to A plus the sum of y, and B star is equal to B plus the number of observations, n. And you can do a kernel density function of the draws that we obtained the first time. Point of this slide being, you can't even really see the difference between the black, the blue, and the green. And that's because there is no difference between them. They're all the same representation of the posterior PDF, but there's certainly a difference compared to the prior PDF, the red line that I obtained by calling the d gamma function with shape A and rate B. So by conditioning on the data, it looks like somebody took the red curve and smooshed it to the left. Both the red curve and the other curves, they all have 1 unit of area underneath them. But conditioning on the data changes the red curve, the prior PDF, into the posterior PDF. In this case, it shifts it left. It makes it more concentrated, around, a little bit more than 2. Whatever. Conditioning reallocates credibility across the parameter space. Conditioning on new data necessitates a reallocation of the credibility across the parameter space data, which is technically from 0 to infinity, but almost all of it is between like 1 and 4. All right. So we're out of time. You can check out the steps that I used to obtain the analytical representation of this. Again, the gamma distribution is naturally conjugate to the Poisson log likelihood. But after this week, there's going to be like no more examples where we're able to take and get a somewhat analytical solution to these posterior things. So we're not going to be able to draw posterior PDFs, whatever. We're just going to be able to get draws from the distribution, the posterior distribution, and then work with those draws. But we'll pick it up more on Thursday and talk about more how to choose these prior distributions, things to think about when doing that. So I'll see you then.